So in this video, I want to talk about forces and Newton's laws of motion, and then I want to talk about each force that we might see when looking at forces in a general physics class. So first of all, forces are just what we think of intuitively as a push or a pull. And the units of forces are measured in newtons, so after Isaac Newton. And we usually write that with a capital N. And 1 Newton is equal to 1 kilogram meter per second squared. So this is kilogram times meters per second squared. And things you should know about forces: first of all, force is a vector quantity. And this means, like all vectors, it has a magnitude and a direction, so the direction matters. Okay, so when you push or pull on something, you have to say which direction you're pushing or pulling on it. And like other vectors, this means we can break it into components. So a force that is at some angle, say it's up and to the right, we'll call it capital F, this force can be broken into, and call this angle theta, can be broken into an x component and a y component. Okay, just like we do with a velocity vector or an acceleration vector. And this leads to a very important thing that we're going to see a lot, is now these forces, because they can, because it's a vector and the direction matters, forces can cancel each other out. So you may have an object, let me do this in white, and you have a force to the right that's equal to F, and a force to the left that's equal to minus F. Okay, so it's, or maybe I should just write F, and it's, you can see it's going to the left. Since these are equal, the total force, or the net force, is going to be 0. Okay, and so this is really important. If you're pushing on an object and someone else is pushing equally as hard in the other direction, it's not going to go anywhere and nothing's going to happen. Okay, so this is really important, and this is why we have to keep in mind that forces are vectors and the direction matters, because if you both push in the same direction, that's going to be a very different result than if one of you pushes to the right and another pushes to the left. So let's talk just briefly about what all the forces are that we might see. First, there are what we call contact forces, and this is most of the forces that we're going to end up seeing. The first one is called a normal force, and a normal force is just a perpendicular force, or a force that is perpendicular to a surface. And so if we have, say, a block sitting on a table, the block is not going through the table because the table is pushing upward on the block. And it's going to be at a right angle to the table. And so sometimes in math and in physics, we call perpendicular, we call that normal. So another word for perpendicular is normal. And that's why this is called a normal force. Okay. And so this is the force that keeps an object from going through the surface. Okay. And we usually write this with a lowercase n. So sometimes you might see it as, let me do this in a different color. You might see it as capital N. I try to avoid using capital N because our unit for force is a Newton, and it's given a capital N as well. So just to help prevent some confusion, I use lowercase n. Then there are frictional forces. Okay, and we'll talk about different kinds of friction forces, but these are also when you have contact with a surface, but these are parallel. These are always parallel to a surface. So if you have a block and you are trying to, let's just say it's moving, it's moving to the right. If there's friction on this table or on the floor, whatever it's sliding along, then friction is going to try to slow it down or try and stop it. And so we give friction this little f, so this little curly f, okay? And friction is always going to be in the opposite direction of motion. So really opposite of your velocity, or the object's velocity across the surface, okay? And then we have tension forces. So if you want to pull something, a lot of times you will use a rope or a cord or a cable or something like that. And the important thing to remember about tension is it's always a pulling force. Okay, so you always attach a rope or a chain or something like that to an object when you want to pull it. But if you stop pulling, the rope or the chain will never push on an object. It will only pull. So as soon as you stop pulling, it kind of goes slack. So this is from a cable, a rope, string, a chain, etc. Okay, and you may see this as either, let me put it over here, as tension with a capital T, or you may just put a force and then a sub T to let you know it's tension. Sometimes when you talk about circular motion, we have T for the period. And so if you use capital T in both places, it may get a little confusing. But you should always know which one it is from context. Okay. And then we have another force from springs. And so springs have restoring forces, or a spring force is called a restoring force. And this is because when you stretch it or compress it, it's always going to try to pull itself back to some original position, what we call an equilibrium position. Okay, so if you compress a spring and let it go, it's going to stretch back out. If you stretch it and let it go, it's going to compress back to its original length. Then we have non-contact forces. So we're only going to talk about one of these in Physics 1, and that is going to be the gravitational force. So gravitational force. The gravitational force is always attractive. So it's always attractive between objects with mass. So it's always an attractive force between two objects with mass. So this comes from Newton's law of gravitation. So with mass. Okay. And we have a special name for this, near Earth's surface. So near Earth's surface, the force of gravity on any object is what we call that object's weight. So weight is another word we use for the gravitational force of the Earth on an object when it's near the surface. And this is a really important part of that. And then there are other forces such as electric forces and magnetic forces. These are also non-contact forces, sometimes called forces at a distance. Forces, and this is typically seen in a Physics 2 class. So what are things that you might want to do with forces? Well, you may want to add them together. It's often that you may have multiple forces acting on an object. Okay, so maybe you have this object sitting on some surface, and you have one force pulling up like this, another pulling to the right. Well, then we can add them together using our rule for adding vectors, either triangle or parallelogram rule. And this is going to be what we call the resultant force. So sometimes This is given a vector r, but I like to use F sub r for resultant force. And this just means add up all of your force vectors, however many you have, or however many you want to add together. And another way to write this that we'll see a lot is when you add a bunch of forces, we sometimes use this Greek letter sigma. So if you see sigma, so sigma, a capital sigma, this means to sum. So it kind of looks like a weird, well actually it looks like an E, but it stands for sum. And you may also see this written as F net, or the net force. So when you add up all the forces together, what you end up getting is the net force. Okay, and so you may see all of these things written in a different way, but they all mean the same things. Okay, and then as always, when we're solving problems, and this is important to remember, we want to take advantage of the fact that forces are vectors, and so we always want to use components when we add forces. So graphically, a picture may give us a good intuition for what's going to happen, but ideally, we're going to use components in order to actually solve the problem and do the math. Okay, so hopefully we can find those in some way. And so our resultant force, or the x component of our resultant force, is what we're going to get by, or FRX, is what we get by summing up the forces in x, or F net x. Okay, so these are all different ways of writing the same thing. We can do the same thing for the y direction. Some of the forces in y, or the y components, and this gives us the net force in the y direction. Okay, and these are just all different ways of writing the same thing. To write the same thing. So depending on what textbook you're reading or how your instructor may write this, you may see it any of these ways, but you should just know that they're the same thing. It's just another way for saying add up all the forces in some direction. Okay, once we have our x component of our resultant force and our y component of our resultant force, maybe we want to find the magnitude or the direction. So you may write this either way. To do that, we do the same thing we do with all vectors. So to find the magnitude, we're going to combine our components using the Pythagorean theorem. Okay, so this forms a right triangle. So FRX squared plus FR y squared. And if we want to find the direction, we do this the same way as other vectors as well. So to get theta, we might use inverse tangent of the opposite side over the adjacent side. And if you want the angle relative to the positive x-axis, this would give you inverse tangent of FRY over FRX. So now that we know what what forces are, we can talk about Newton's laws of motion. And these laws tell us how forces cause motion to change. So typically you start off physics studying kinematics, or just describing motion in terms of velocity and acceleration and where the object is. But we never talk about how objects obtain some acceleration or why they're moving like that. We just kind of describe it. And forces really tell you why. And Newton's laws are what governs how forces change an object's motion. So the first law is sometimes called the law of inertia. Okay? And the law of inertia just says that an object is going to move with constant velocity. which also means no acceleration unless there is a net force acting on it. So if you add up all of the forces and there's still a net force, then the object is going to accelerate. Otherwise, it's going to keep going in a straight line at the same speed. Okay, so that's what it means to have constant velocity. You're not changing direction, you're not speeding up, and you're not slowing down. Newton's second law, this is probably one of his most famous laws, the one that comes up the most in solving problems. And it's the law of motion, and this is just continuing from the first law. It says that a net force will cause an acceleration proportional to the force, so proportional to that net force, and inversely proportional to the mass of the object. Inversely proportional, just do prop, to the mass. Okay? And so this means, this is sometimes written as the force, the net force, is equal to the mass times the acceleration. Okay? And a better way to write this, to really understand Newton's second law the way it's written, is to rearrange it for the acceleration, or the acceleration is equal to the net force divided by the mass. And so this means if you increase the net force acting on this mass, you're going to make it accelerate at a greater rate. If you increase the mass, you're going to decrease the acceleration. Okay, so if you push just as hard on an object that's heavier, or a more massive object, it's not going to accelerate as much. If you push with a harder force, then it will accelerate more. Okay, so this is this relationship between acceleration, the net force, and the mass. The final law is the law of action and reaction. So you've probably heard this. The first law is an object at rest stays at rest. An object in motion stays at motion. So you've probably heard it that way. Newton's third law, you've probably heard for every action there's an equal and opposite reaction. So I'm going to say it as forces occur in pairs, okay, that are equal in magnitude but opposite in direction. Okay, and really what this means, let me zoom in a little bit. This means is that if I have two objects, object A and object B, and say they're pushing on each other, so say they're pushing on each other some way, this means that the force from A on B, so the force that A is pushing on B, must be equal to the force of B on A, except it's in the opposite direction, so it's negative. So this one's in positive x, and this one's in negative x. So positive x, negative x. Okay? And so these are sometimes called action-reaction pairs. So these are called action-reaction pairs, and it helps us identify all the forces that are present, because we know that if A is pushing on B, that must mean that B is pushing on A. So Newton's first law is called the law of inertia, but we don't know what exactly this word inertia is, so we'll define it. Inertia is the property of objects to resist changes to their velocity. So objects don't want to change their velocity, and that's why it requires forces to change their velocity. And the way we measure inertia is by the mass. So that's why mass shows up in Newton's second law. This just means the more mass, the more inertia. So the more massive an object is, the more it wants to keep going at its velocity in whatever direction it's moving. And if it's more massive, we're going to have to apply more force to get it to accelerate. So if we want to change its velocity, so change its direction or speed it up or slow it down, we're going to have to apply more force because it has more inertia or more resistance to this change. Okay? Then there's an important idea called equilibrium. So this goes back to when we first started talking about forces, and I said they can kind of cancel each other out because of the vector nature of forces. And so this means that when we sum the forces, they equal zero. And if the forces equal zero, then I can write Newton's second law. So sum of the forces equals mass times acceleration. If this all equals zero, then this must equal zero and this must equal zero. Well, I know my mass isn't zero, so if the net force is zero, that must mean my acceleration is zero. So this means you're going to move at constant velocity or you're not going to accelerate. So no acceleration. Okay, and this also works component-wise. And this is what we're going to use in a lot of our problems. We're going to sum up the forces in the x direction, and it's going to be zero in equilibrium. And so that's going to tell us that we're not accelerating in the x direction. Same for the y direction. If we sum up the forces in y, that'll equal zero. And the acceleration in the y direction will equal zero. We write Newton's second law again. So F equals ma. Hear that said a lot. So this is Newton's second law. Both of these have vector hats. So both force and acceleration are vectors. And so this means that the direction of acceleration is equal to the direction of the net force. Okay? Because the acceleration on the right side has to get its direction from something on the left side, and the only vectors are the force and the acceleration. So their directions have to be equal. Okay? And this is the acceleration of this mass. So we only use a single object at a time when we're looking at Newton's laws. So a single object at one time. Okay? So when we sum up the forces and set it equal to mass times acceleration, it is these forces that make this mass, so this guy, accelerate with this acceleration. Okay, so if you have multiple masses, you need to do Newton's second law for each of them, and you can sum up the forces on each mass, and then you'll set it equal to that object's mass times its acceleration. Okay, so when you have multiple objects, you have to treat them separately. So now I want to talk through more in detail about some of the specific forces that we're going to encounter. And so I want to start with the normal force and tension forces. Okay, and so if we look at all of our forces, a lot of them have equations. So I'm going to write all of the forces that can be represented with some equation. Okay? If I do that, we have the weight. So the weight is equal to mass times gravitational acceleration. Okay, so this is a definition, and we can derive it and show where it comes from. Then we have the force of friction, and this is given by an equation, coefficient of friction, mu k, times the normal force. We have static friction, which is less than or equal to the coefficient of static friction times the normal force. We have the force of gravity, just in general, which is big G, some constant, universal gravitational constant, times the product of two masses over the distance between them squared. And even when you go on to electricity and magnetism, you get other forces like the electric force that look similar to gravity. Some constant times the charges, so Q represents the charges over the distance between the charges squared. But all of these forces have equations. There are some that do not have equations. And so you can guess two of those are normal force and tension. So a lot of times students say, what is the equation for normal force? What is the equation for tension? But there's not one. Okay, so you have tension, you have normal force, and these are going to depend. It's going to depend on the physical scenario that you're looking at. And the way we find them is we use Newton's laws. Specifically, his second law, F equals ma. We sum up the forces, and then we can use what we know to solve for the tension and the normal force. Normal force if we just look at some different cases, if we have a block on some surface, the normal force is going to be pushing straight up, perpendicular to that surface by definition. And so if we were to draw a free body diagram for this block, we would have a normal force that's up and the weight of the object would be straight down. And so we could do Newton's second law and sum up the forces in the y direction, since everything's acting in y. And we would get a positive normal force, since it's going up, minus the weight, since it's going down. And we would set that equal to the mass times the acceleration in the y direction. And since the acceleration is 0, because the block's not moving up or down, we get that this is equal to 0. So this tells us, by moving the weight over, that the normal force is equal to the weight, or just equal to mass times gravitational acceleration. Okay, so now let's look at another example, same block, but now we want to apply some force down. So we're going to push down on the block. So now we do a free body diagram, and the normal force is still going to push up on the block to keep it from going through the floor. But now we have this downward pushing force plus the weight of the block. So if we sum up the forces in the y direction, we have a positive normal force minus this pushing force and minus the weight. And again, that's going to equal 0, sum to 0. And so if we solve for the normal force, it's going to be the weight plus this pushing force. So that means the normal force is going to have to counter or cancel out all of this force now. So now it just got a little bit bigger. So we added this pushing force to the weight, and that's equal to the normal force. We could also go the other way. Maybe we're pulling up on the box. Okay, now again, we do a free body diagram. Now we have the normal force from the floor pushing up, but we also have this pulling force. And then in the negative y direction, we have the weight. So if we sum up the forces in the y direction, we get the normal force plus this pulling force minus the weight sums to 0. We saw for the normal force, we get the weight minus this F pulling force. And so this tells us that the normal force from the surface doesn't have to act as hard. It only has to support whatever's left over after we subtract off this pulling force. So whatever part of the weight is left over, that's how hard the surface is having to fight to keep the object from going through it. So in all of these cases, your normal force depends on the scenario. It depends on the other forces that are occurring and that are exerted on your object. So similarly, we can look at tension. So we can use a tension example. If we have a block, this is a roof or ceiling, we have a block, so block A, supported by some cable, some rope or something. If we draw a free body diagram, then the weight of this block is going down, and then this cable is pulling up on the block, keeping it from falling. Okay, so if we sum up the forces in the y direction, we have tension going up minus the weight, and that equals the MAY, but it's not going anywhere, so this is just 0. And we get the tension is equal to the weight, or the mass of the block times gravity, similar to the way what we had with the normal force. But now, if I were to add another block on top of it, or to the bottom of it, now this same cable is having to support even more weight. So if we draw the free body diagram, we have the same tension going up, but now it's having to support the weight of A plus the weight of B pulling down on it. So if we sum up the forces in Y, we get the tension minus the weight of A minus the weight of B equals 0, sums to 0, and we get the tension is equal to the weight of A plus the weight of B when we move them to the other side. Okay, so now this tells us that the tension has to support both of the weights. Okay, so it has to be equal and opposite. Well, what if we, instead of having 2 blocks, maybe we take 1 block and then we have 2 identical ropes attached to it, and so they're both pulling up. Well, now if we draw the free body diagram, since these are identical, there's going to be 2 tension forces pulling up, and we're going to have the weight of this block pulling down. Now if we sum up the forces, we have 2 tension forces going up minus the weight, and that's going to sum to 0. So now we have the tension equals 1/2 of the weight. Okay, because now it's spread out. So again, the force of tension in each case depends on the scenario. It may change, it may go up, or it may go down, and it really just depends. So you have to add up all the forces and draw your free body diagram if you really want to find the magnitude of your normal and tension forces. So now I want to talk about the directions of tension and normal force. So tension is always going to pull away. So it's always away from the object. Again, you never have a rope push on you. Once you stop pulling, the rope goes lax. Okay, it relaxes, it goes flaccid, and it's no longer taut. So a cable or a rope will never push on you, it will only pull. And then for normal forces are always perpendicular, or another word for that is normal, to the surface. Okay, so if I draw some examples, if you have a block A connected to a block B by some cable, it's on the ground, and say this cable's pulled tight, this cable's pulling away from block A. I'll do that in a different color. It's pulling away from block A here, but if we were to look at block B, it's also pulling away from block B. Okay, so it is always away. Okay, if we have a block on a flat surface, we want to look at the normal force. The normal force is going to be straight up, perpendicular to this surface. Okay, so this makes a right angle. And so if we have a slope or a slanted surface, so it's slanted at some angle, and we put our block on it, it's still going to be perpendicular. Okay, so you would not want to draw your normal force like this. This would be wrong. Okay, always draw it perpendicular. Okay, now I want to talk about weight and mass. So these are different, and a lot of times they get confused. Mass is a measure of how much inertia an object has, and this is something that does not change. So you have the same amount of inertia because you have the same amount of mass. Okay, your mass never changes. In a lot of classes like physical science or chemistry, you may have learned that mass is how much stuff you are. So how much atoms an object has is its mass if you added them all up. And mass is measured in units of kilograms. And it's something that never changes, while your weight is slightly different. Weight is a type of force, and specifically is the force of gravity. And it is the force of gravity near Earth's surface, actually near the surface of anything. Your weight on Earth would be near Earth's surface. And this is given by this equation. The weight is equal to mass times gravitational acceleration, but this may change. Okay, specifically if you're on another planet and you're not near Earth's surface but the surface of another planet, you may have a different gravitational acceleration. So little g is specifically the gravitational acceleration of the Earth, but it may have a different value on another planet. Okay, and since since weight is a force, it has units of newtons. Capital N, and again, 1 newton is equal to 1 kilogram meter per second squared. So this is where mass is part of, not meter, is part of weight, but they are not equivalent. In order to get the weight of an object, if you know its mass, you need to multiply by gravitational acceleration. So it's really important to remember that mass does not change. Okay, while your weight depends on your distance from Earth. So if you're near Earth's surface, then your weight is always just your mass times your gravitational acceleration on Earth. But maybe you're on some other planet, then your weight on that other planet would be your mass, which doesn't change, times your gravitational acceleration on that planet. So we may call it planet X, whatever it may be. Okay? Your weight is also equal to the force of gravity in general. So this is the force of gravity from Newton's law of gravitation. And it's given by this formula where big G is just a constant. And then you have the product of two masses. So this is your mass times the mass of the Earth. And you're attracting each other. And this force of gravity depends on the distance between the two masses. So if you were on the surface of the Earth, this would be Earth's radius, because that's how far away you are from the center of the Earth. But if you're some distance above the Earth, then you would just put that distance from the center of the Earth as your R. Okay? And so your weight, no matter if you're on some slope, when your normal force may change, it's going to be in a different direction. Your weight is always going to be straight down, because that's the direction to the center of the Earth. So if you're on a flat surface, it's going to be straight down. And it doesn't matter, it'll be straight down no matter what. So now let's talk more about this gravitational force. The gravitational force, just in general, okay, is F big G, so big G m1 m2 over r squared. Gravity always acts between two masses, so two masses are always pulling on each other. So the force of gravity is always attractive. So if you have two masses, m1 and m2, they are going to attract each other. Okay, big G, this is just a universal constant. So it's equal to 6.74, I believe, times 10 to the minus 11. You may have to look that up. Newton meters squared per kilogram squared. Okay, and then this R is just the distance between the centers of the two masses. So m1 and m2. Okay. And now we said that your weight is the force of gravity when you're near a surface, and then this is also the force of gravity just in general. So that must mean that we should be able to set them equal to each other and get the same thing. So we said the weight is your mass times little g, and the force of gravity is big G times your mass times the mass of the Earth over the radius of the Earth squared. Well, if you notice, your mass shows up in both terms, and now you get the value of little g. So this is G equals big G times the mass of the Earth over the radius of the Earth squared. So in kinematics, when we got gravitational acceleration equal to 9.8 meters per second squared, you can actually find that value by plugging in this constant big G, the mass of the Earth, and the radius of the Earth into this equation. And this is where it comes from. If you wanted to find the value of gravitational acceleration for another planet or even the moon, you would just need to plug in the mass of that planet or moon and its radius. And you could get gravitational acceleration for that planet. And then you could calculate your weight, what your weight would be on that planet, since your mass doesn't change. Now I want to talk about spring forces. So spring force follows what's called Hooke's law, and it says that the spring force, or the force of that object, is proportional to its displacement from some equilibrium position. Okay, so this K is just a proportionality constant, and it tells you how stiff your spring is. Okay, so this is called the spring constant, and it gives you the stiffness of the spring. Okay, so a really stiff spring would have a big value of K, and a really lanky kind of spring that's not stiff would have a small value. Okay, you may also see Hooke's law or spring force written as minus kx, so this shows up in some textbooks too. And here, the delta L and the x, this is just the displacement, so how much you have stretched the spring or compressed the spring. Okay, K again is the spring constant. In this, the reason why you see this minus sign in this formula is because this tells you the spring force always opposes the displacement. And so why isn't this minus sign in the first equation? Well, when we use this equation, we're just going to plug in the direction by hand, because we know if the spring was stretched, it's going to have a force in the opposite direction of the direction it was stretched. And if it was compressed, again, it's going to be in the opposite direction. So we can just put that in by hand. Okay. So this relationship is called Hooke's law, and it's for objects with restoring forces, or forces that restore them to equilibrium. So you can think of stretching or compressing a spring, or you can think of a rubber band. If you stretch a rubber band and let it go, it's going to come back to its original size. Okay, so if we had a horizontal spring and it's been compressed, so it's squeezed, so it's being squeezed this way, we'll call it delta L, and it's compressed, the spring force is going to try to push the block out until it uncompresses itself. If on the other hand we had a stretched spring, well, now it's being stretched out to the right, and the spring force is going to, if we let this block go, the spring force is going to pull it to the left. Okay, and then we could also hang objects from a spring vertically, and this object is going to pull the spring down, so delta L is going to be down, so the spring force is going to be up. It's going to pull the object up. Okay, so in horizontal springs we may call this delta L, delta X, and then if it's a vertical spring we may call the displacement delta Y. Okay, the last force I want to talk about is friction. So friction is a contact force that is parallel to the surface, and it opposes motion. So it tries to stop an object or slow it down, or it tries to keep it from moving in the first place. So turns out friction is proportional to the normal force. Proportional to the normal force. So if you have ever tried to push something across the floor, and then someone came and pushed down on it, they are increasing the normal force when they push down, and then it makes it harder for you to push the object sideways. That's because you're increasing the normal force, so you're increasing the amount of friction. If you're trying to push something across the floor and somebody picks up on it a little bit, then it gets easier because they're decreasing the normal force, and so they're decreasing the amount of friction. Okay, so it kind of makes sense. The normal force really tells you how much contact there is, and so if there's less contact, there's going to be less friction. If there's more contact, there's going to be a stronger frictional force. And so we divide friction up into two different types. The first is kinetic, and so we give this a little subscript k, and it's equal to this constant mu k. So this is a Greek letter mu, and then this is the normal force. So mu k is the proportionality constant, okay, that tells you how strong friction is, or how much friction there is between two objects. And this is the type of friction that slows a moving object, or fights a moving object. Okay, so kinetic, when you see the word kinetic, you should think moving. Okay? And this is just a number that tells you how strong the friction is between those two materials. The other type of friction is static friction. And when you see static, you should think not moving. Okay, so we give that a subscript s, and it is less than or equal to its own coefficient, again, times the normal force. So this is friction that prevents an object, or tries to prevent an object, from moving in the first place. From moving from rest. Okay, and so what is this less than or equal to sign doing here? Well, static friction can vary up to some maximum value. Its maximum when it's equal to this coefficient of friction times n. So I guess I will write these are coefficients of friction. So we call it coefficient of kinetic friction, coefficient of static friction. And when it's equal to this, then it's at its maximum value. But the way you should think about this is if you push on a really heavy object and there's friction, if you push on it a little bit, it's not going to move. And that's because friction is opposing however hard you're pushing. But if you push a little bit harder, it's still not going to move. And so your friction has increased to keep the object from moving. And as you push harder and harder, friction is going to fight you more and more to keep the object from moving until it reaches some maximum value. Once you push harder than this maximum amount of force from static friction, then the object is going to start to move if you push any more than that. Okay, so the force of static friction can vary up to some maximum value. Okay, and then once you push beyond that max value, the object will start to accelerate and move, and then you're going to start dealing with kinetic friction. Okay, and so that's a little brief overview of all the different types of forces that we might see in general physics.